Okay, I hope that you have enjoyed your holidays. Let me just complete what is left a little bit from the previous chapter under the title of limits. So I call it second visit because we already know actually how to calculate limits, but a particular type of limit. But what you learn there is more or less the same thing that we want to do here. So here we want to talk about what is the meaning of this. We say the limit of a function f of x when x goes to a becomes L. What is the meaning of this in mathematics? Of course, understanding limits very rigorously, if you want to do it, that is actually quite beyond the scope of the high school. You have to go to math probably in the university to learn very good about these things. But I will try to tell you what is the meaning of this. We already know actually more or less what does it mean. When you see this symbol, it means that when I am making x close and close to this number a, the values of my function are getting closer and closer to the value L. Yes? For example, when I say the limit of 2x plus 5 when x goes to 1 or approaches or tends to 1, the answer is 7. And then be careful here, I am putting exact equality, but you need to interpret this equality in this way. So first of all, I told you that what is the meaning of this symbol? When I write x approaches 1, it means the value for x is getting closer and closer to 1, but you are not allowed to stand exactly at 1. That is the point. So this should be interpreted in this way. When you see this symbol, this means that x is very, of course this is a little bit vague, what is the meaning of very here? This is very, x is very close to 1, but x is not equal to 1. So, of course, I cannot talk a little bit about how much is very, but this you need to know. When I say x approaches 1, it means that, for example, x is not 10. We already talked about this, if I remember, Gustav asked some questions about this. But here, I don't know, I want to keep it intuitive. What do I mean by very is not very clear. How much is very, yes? But one thing is important is that x is not equal to 1. So now, is it reasonable to say that when x is close to 1 and not equal to 1, the value of this function becomes close to 7? Yes? Why? Because if x is exactly equal to 1, if I replace this x with 1, the answer becomes exactly 7. And of course, then it becomes clear that if I am very close to 1, but not equal to 1, the value that I get is close to 7. So in principle, if you want to understand the behavior, it means that at the level of high school, this is the only way that you can convince yourself. So you write your x, you write your function f of x equals to 2x plus 7, and then start calculating the value of your function for values of x that are close to 1 but not equal to 1. And then try to see what the pattern appears. Is there a number that these numbers are approaching to? So it might not be easy to calculate exactly what's going on, but for example, let me put, I don't know, 0.9. This number is actually a number which is close to 1. Okay, yes?
Did you mean to write 2x plus 7?
No, sorry. Thank you. 2x plus 5. Thank you.
Okay.
Okay, so if I put 0.9 here, so I have to calculate 2 times 0.9 plus 5. So what do I get as the value? It becomes 6.8. Yes? If I get even closer, 0.99, so what happens? I put 2.99 here plus 5. So what will be the answer? It would be 6. How much?
998.
998.
Yeah.
Did you calculate using
Oh,
calculator?
sorry.
Only 98.
9, 8.
Yes.
I added an extra.
Yeah. So that is this number. And if I get it closer, for example, 0.999, you see I am allowed to approach to 1 as much as I am pleased, but I am not allowed to be on 1 at 1. So if I do this and I calculate this once more, I think you will get 0.998 again. I'm not sure about that, if you can confirm.
Yes, you
that.
do.
Yes, okay. And then you see that, of course, here I have chosen from numbers. By the way, that's also important. I am approaching number 1 with lower values. Yes? This is not in your book, but at least it is. I want you to understand. Sometimes people put a plus or minus on top here. Yes? This is not in your book, but I just want to know about this symbol. If you see this symbol here, this means that x is approaching to 1, but from the lower values. This minus has nothing to do with minus and positive signs. It means that x is always less than 1, but very close to 1. Yes? So here, this means that this way of thinking means that I am approaching to 1 from the lower values. I put a minus sign here. You don't need to learn this. This is not in your book. But I want you to understand, if you see a minus on top, it means from the left-hand side, from the lower values, I am approaching to 1. But now, let me approach to 1 from the higher values. And the symbol that people use is this. I put a plus sign on top. This tells you that I am getting closer to 1, but I am always above 1. This means that I am getting closer to 1, but I'm always below 1. Yes? So for example, one number that I can choose is 1.1. 1.1 is close to 1, but it is higher than 1. If I put 1.1 here, then it becomes 2 times 1.1 plus 5, and the answer will be 7.2. Yes? And then if I make it even closer, but it's still higher values, so then it becomes 1.01, for example. Still I am above 1, but I am closer than the previous step. So then it becomes 2 times 1.01 plus 5, and if you calculate that, it becomes 0.072. But anyway, so if I want to understand this behavior, this part of the table tells you that x approaches to 1, but from the right side. But one thing becomes clear intuitively, not precisely. Hopefully by looking at these produced numbers, you see that when I am getting closer and closer to 1, these values are getting closer and closer to a particular value. And what that value is, by intuition, you see, this number is getting closer and closer to which number?
1.
No,
5.
7, the whole number.
Okay.
Yes? And this number is also getting closer and closer to 7. So it doesn't matter in which direction I am approaching to 1. In both cases, the values of the function is actually getting closer and closer to 7. This behavior is summarized under this symbol. So this is, be careful. This equality will never be achieved unless I stand exactly at 1, which I'm not allowed to. But I put equality, not approximation. Be careful. So when you see this symbol is a summary of this table. So you need to be able to interpret it in that way. That is the most that you can understand from this symbol. This tells you that I can get closer and closer. If you want to understand it quite well, this is the way. This number can be made close, can be made arbitrarily close to 7 under this condition that I make myself close enough to 1. Yes? If I want to be a distance 0.2 from 7, I need to keep my distance from 1 by 0.1 or less smaller. But if I want to be closer, if I want to be very closer to 7, I have to be closer to 1 as well. So that is what I want you to understand. We always write equality sign, but this symbol that you see means the whole table. Yes? Okay, but of course you see that this is the very boring way of doing things. So we need to use algebra if possible to calculate limits of different functions. And we have already done that. Okay? So there are some theorems that I want you to know. So if you have the limit of a function f of x when x approaches to a is L, and you also know that the limit of another function, say g of x, when x approaches to the same number a is, say, for example, is m. So what is the meaning of this? It means that when I am getting close to a, f of x is getting close to L, and when I am getting close to a, g of x is getting close to m. Now if I ask you, intuitively, these are theorems. If you want to do them properly, you have to prove them mathematically. But here, that would be quite advanced. Let us do it intuitively. Can you guess what will happen for this one? If I give you the limit of f of x is L, if I give you the limit of g of x is m, in both cases, x approaches the value a. Now I am asking you, what do you think would be the limit if I add these two functions and calculate the limit at the same number a? Yes?
Would it be L plus n?
Yeah, it is natural, yes? Because this means that f of x is getting close to L. This means that g of x is getting close to m. So if I ask you what is the value that f of x plus g of x is getting close to, it is clear it should be L plus m. Yes? So then it means that this is L plus m. So in other words, the limit of the sum of two functions is equal to L, which is the limit of the first one, plus m, which is the limit of the second one. Yes? So you don't need to look the middle one. So this is one theorem. This is intuitively correct, but if you want to prove it rigorously, it is hard. But just take it for granted here. The limit of the sum of two functions is equal to the limit of the first one plus the limit of the second. And if I have this difference, this would be the difference. Yes? And if I have the limit of product, what do you think will happen? Lm? Yes, it would be Lm. So this means that this becomes the limit of the first one multiplied by the limit of the second one, which, as you said, is Lm, but I just dropped that. I don't need Lm. Here you don't need to look at it in this way. And there is also another thing, the limit of what happens for f of x divided by g of x. Yes? What will happen for this one, do you think? You see, the above one is getting close to L. The denominator is getting close to m. Now I am asking to which number is this fraction as a whole getting close to? Yes?
Is it just L divided by
L divided by m, or instead of writing L, I can write what? Limit of f of x, limit by g of x. But there is one condition that I have to be careful about. What that condition is? Yes? This one?
That it's not equal to 0.
0. Because it might happen that this number accidentally becomes 0. Then, of course, I am not allowed to divide by 0. So here, m should not be equal to 0. So this is something very natural. You really don't need to memorize something. If you want to add functions and then take the limit, don't care, don't be worried. Just take the limits and then add. If you want to subtract, calculate the limits, then subtract. If you want to multiply and calculate the limit of the product, don't worry. Calculate the limit of each part and then multiply. And then if you want to calculate the limit of a quotient, don't worry, just calculate the limit of the numerator, the limit of the denominator, and then divide the values. If the denominator is 0, the limit does not exist. So that is, be careful. So if in some case this m is 0, what do you answer? You will say that the limit does not exist. Okay. Okay, so that is very simple and very natural, but sometimes we have something that we have to be careful about, yes? Yes. Okay, now there are some limits that are called indeterminate. This is a mathematical terminology that I want to talk about. So why this is the case? Let us see what happens. And there is another word that I want you to learn. It's called infinitesimal. So infinitesimal is the mathematical term that we use for negligible. When we say it's a quantity is infinitesimal, it means that it is very, very small. Yes? So that's another word that I want you to learn. Okay, so let me ask you something. If I take 0 and then divide it by 0, what do you think about this? Is this a fraction? Is this fraction defined or not?
Undefined.
It's undefined. The reason that I bring it up, because even in your book, this is the common in literature, in mathematics, they call this indeterminate, which is wrong. Yes? Only after you learn what they mean, then you can use that word. Okay? So, indeterminate is not a good word to use this. If I ask you what do you say about this, there's one good word for it, and that is called undefined. This expression in mathematics is undefined, not indeterminate. Okay? But let me ask you something. If I write infinitesimal, so let me write infinitesimal, and then divide it by 0. What infinitesimal, it means that is a very, very small number, close to 0, might be positive and close to 0, or might be negative and close to 0. Whatever it is, I divide it by 0. What this expression is called?
Indeterminate?
No.
Undefined.
Undefined again. So I assume that you have, in the exam I give you this number, it's negligible, it's infinitesimal, for example, and I divide it by 0. What is this one? You say immediately this is not defined. So this is not defined. This is not defined. Okay. Let me fix this. And now let us do the other way around. I put 0 on top. I put infinitesimal in the denominator. What do you think about this? Is there something that I can say about this? Is it undefined? Or if it is defined, what the value is? Or can I say something about the value or I cannot?
0.
It is 0. So this is not defined. I have 0 divided by a very, very, very small number. Who cares? Yes? 0, 0, 0, 0, 0, 0, 1. If I ask you what the value of this, definitely without doubt is 0. So 0 divided by infinitesimal is 0. So infinitesimal divided by 0 not defined. 0 divided by infinitesimal is 0. What they call indeterminate is infinitesimal divided by infinitesimal. This is the meaning of the word indeterminate, which in most of math literature, they write 0 over 0 is indeterminate. But I want you to understand, what is indeterminate is infinitesimal divided by infinitesimal, even though people use 0 over 0. Because probably they are lazy to write so much, they write 0 over 0.
Also, if the values of the infinitesimal numbers are the same, then the answer will be wrong.
What? But the point is that that's exactly why it's called indeterminate. Because depending on the behavior of the function, the value that you get is quite different. So for example, if I ask you the limit of x over x when x goes to 0. First of all, I want you to understand, is it undefined or is it of this type? I want you to understand this limit of x divided by x when x goes to 0. If x goes to 0, approaches to 0, it is very, very close to 0. So it is infinitesimal. But it is not exactly equal to 0. So the numerator is infinitesimal, the denominator is also infinitesimal. So this is indeterminate. This limit is indeterminate. Okay? But what would be the value of the limit? So what is the meaning of that? This means that you go, if you want to understand, you have to write this and you have to write this. For example, let me put x equals to 0.1. What would be the value of this function? If I put x equal to 0, you need, so no worries. Sorry, no worries. Okay, so let us calculate this. If I put 0.1, what is the answer here? 1. If I put 0.01, the answer is 1. So, but I am not allowed to stand on 0 because I told you this means that you can go close to 0, but you're not allowed to stand exactly at 0. So this is not possible to be this. But if I go even further, what would be the answer? 1. And even if I go a little bit negative values, for example, minus 0.1, what would be the answer again? 1. So what is this limit again? So you see, these numbers are approaching. They are exactly the same number. So this limit is equal to 1. So you see, infinitesimal divided by infinitesimal gave me 1. But let me ask you this question. For example, x squared minus 4. We had something like this before. X minus 2 and x goes to 2. If you want to categorize this limit, can you also categorize it under this title of infinitesimal over infinitesimal? Yes or no? X approaches to 2 means x is very close to 2, but not equal to 2. So the denominator is an infinitesimal. Yes? Because x is very close to 2. If you subtract a number very close to 2 and 2, it becomes a very small number. It becomes negligible. The terminology is infinitesimal. Okay, so the denominator is an infinitesimal number under this circumstance. What happens for the numerator? Is it also an infinitesimal or not? If x is exactly equal to 2, x squared minus 4 is exactly equal to 0. You are not exactly equal to 2, you are very close to 2. The numerator also becomes infinitesimal. Do you agree? Yes. So this means that even though this limit and this limit are different, but both of them can be categorized under the title of infinitesimal over infinitesimal. But now let me calculate this limit. Can I put 2 right away here? Can I calculate the limit of the numerator divided by the limit of the denominator? No, because the limit of the denominator is 0. So what can I do? We learned about this before. So I factorize this, x minus 2, x plus 2, and then I divide it by x minus 2, x goes to 2. Am I on the safe side to cancel these things? First of all, yes, because both of them are factors, and factors can be simplified if needed. The second thing is that I am sure that this number is not 0 because x is not equal to 2. It's close to 2 but not equal to 2. But then what happens? This becomes the limit of x plus 2, x goes to 2. So what happens here? What's the answer? What's the answer?
4.
4. So you see, this is the reason that we call it indeterminate. So if I ask you what type of limit you are facing here, you say infinitesimal over infinitesimal, the answer is 1. What type of limit you are facing here, again infinitesimal over infinitesimal, but the answer is 4. So this means that this infinitesimal over infinitesimal is indeterminate a priori. You have to calculate and you get different answers based on the behavior of the function that you are investigating. So that is why it's called indeterminate. And then indeterminate, usually people call it 0 over 0 is indeterminate, but I want you to understand that is a sloppy language for making it quick. But the one that is infinitesimal over infinitesimal is indeterminate. Sometimes might be I also use it 0 over 0, but I want you to understand this is not indeterminate, this is undefined. Yes? What is indeterminate is that if I have two negligible numbers and I want to divide them, depending to the behavior of the function, the answers might be quite different. So that is why we cannot determine it. It is indeterminate. Yes? And there are other types of indeterminate forms that you will study in the university.
I moved the camera again.
So for example...
Babak, I moved the camera. Is it fine?
Okay, any questions? So this is from conceptual point of view. So I want you to understand these differences. So, and we all the limits, now that you know this terminology, if you go back to the derivative part, all the limits that we calculated were of this type. Why is that? Because do you remember what was the definition of the derivative? F prime of A was the limit of what? F of A plus H minus F of A divided by H. H goes to 0. Agreed? Mm-hmm. But now let us look. What is the denominator now? H approaches to 0. So if I ask you what is the denominator, I hope that you agree it's an infinitesimal. Yes? Now, if I put 0 here, this becomes f of a minus f of a, which is exactly 0, if h is exactly 0. But I am not allowed to choose exactly 0 for h. I am allowed to choose very negligible numbers for h. So the difference between this expression and that expression becomes negligible, because a plus h and a will be approximately the same if h is very small. If these two numbers, if the inputs are very close, we expect more or less that the values of the functions are also very close. So this means that the numerator is not exactly 0, but very small number. The denominator is also a very small number. So in most cases, this limit, and in all cases that we consider, this limit is infinitesimal divided by infinitesimal. So even if we didn't name it, so that's not something new. I want you to understand this terminology, but you already work with it, with the concept. All the limits that you calculated when we were dealing with derivatives was of this type, infinitesimal over infinitesimal.
Just a reminder, how did you get 4? I just need a reminder.
I put 2 here. Okay.
Oh.
Yes. So again, why this is the case? Because I am saying that what the value of this function is getting close to, if I make x very close to 2.
Okay.
That becomes 4, yes? Okay, so here, I want to, all the limits that we calculated was this type of limit, but you see that this limit is different from this limit. So, but the techniques and tricks are more or less the same. So let me just practice something, okay? So I will give you an example here. Determine the following limits. So number 1, so limit of, for example, the third root of 3 to the power of x5 minus 2x plus 1, x goes to 1. The reason that I brought this example first, because I want to remind you of what I mentioned when I was teaching you the derivative. Do you remember the trick I told you about calculating limits? was to put that number there. If something strange doesn't happen, that number is exactly your number, yes? So here, if I want to calculate, the first thing that I do is to replace x with this value. So is it working or not? So this becomes the third root. Instead of x, I put 1. And then calculate. If this indeterminacy doesn't happen, or if the denominator vanishes, or if this is the even root and the root under the square root is negative, I'm not allowed to write this number. But none of these things happening for this case. Yes, so the answer would be the third root. This is 2 minus 2 plus 1. So this becomes the third root of 1, and the answer is 1. The only thing that I have to be careful if when this happens, or I have an even root, under that root becomes a negative number, which is not defined, or if I have a fraction and the denominator becomes 0, then that is not defined. In other cases, usually you will not get such a question in the exam because they are very easy, but it doesn't mean that if I give you this in the exam, you are not able to solve it because this seems complicated. No, this is even simpler. Yes, you just put the number there and nothing strange happens. That number is your limit. Okay, but let me now start practicing a little bit more about these type of limits. That is today's lesson. So number 2, so calculate this limit. X squared minus 5x plus 6. X squared minus 4. X goes to 2. So what type of limit is this? This is an indeterminate form of this type. Why is that? Because if you plug 2 instead, what happens for the numerator? It becomes 0. What happens for the denominator? It becomes 0. And that is exactly why people call it 0 over 0 is indeterminate. But that is not exactly 0 because I am not allowed to put exactly 2. When I put a number close to 2, the denominator is not exactly 0. It becomes an infinitesimal. And the numerator also becomes infinitesimal because it becomes 0 if I'm standing exactly at 2. I'm not standing at 2, so that would be close to 0. So infinitesimal over infinitesimal. In a sloppy language, I would say that this is indeterminate of this type. Yes? So it means that I have to lift this determinacy. I have to take it away. How? Here you need to learn this trick. If I have polynomials, you have to learn how to factorize them. So let me factorize. What is the factorization of the numerator? The denominator is very simple. What is that? The conjugate pattern, yes?
Yes.
And what is the factorization of the numerator? I hope that you haven't forgot that, yes?
X minus...
Yeah, I put an x here, an x there, and I ask myself, I need two numbers whose sum is minus 5, and the product is 6. If that is possible, for these small numbers, I always recommend you this. Otherwise, you have to go to the general trick. So what are those numbers?
3 and negative, no.
X minus 2, X minus 3.
Yes. Minus 2 and minus 3 are those numbers. Why? Because minus 2, minus 3 added, it becomes minus 5. Multiplied, it becomes positive 6. So then, x goes to 2. And now you really understand what was the culprit of indeterminacy here. X minus 2 was the reason. Yes? And now that is going away. And then what is left for me is x minus 3, x plus 2. And then I send x to 2. Okay. So do I have problems here? Is this indeterminate? You see, no. It's no longer indeterminate. When it is not indeterminate, you are on the safe side to put the number in. So then it becomes 2 minus 3 divided by 2 plus 2. So the answer is minus 1 over 4. That's the answer. So you see, if I ask you what type of limit is this, in a sloppy language you say 0 over 0. What type of limit is this limit is 0 over 0. This is also 0 over 0. But the answer here is 1, the answer here is 4, the answer here is minus 1 over 4. It's indeterminate. Yes, that's why it's called indeterminate. Any questions here? Okay. Another example, these type of examples are simple. Another type of example is containing surd signs, yes? So limit, for example, let me write a square root of x minus 3 divided by x minus 3, x minus 9, sorry. X minus 9 when x goes to 9.
8 minus 3x side.
Yes, it's not. So what type of limit is this limit? Is it of this indeterminate form that we are studying right now? Yes. Because you put 9 in the denominator, it becomes 0. You put 9 in the numerator, square root of 9 is 3, 3 minus 3 is 0. So that is also 0 over 0. But be careful, this is sloppy language. That is infinitesimal divided by infinitesimal. So that is indeterminate. But the trick you need to learn, we had this trick before when I was doing derivatives, if you remember. How many of you remember? How can I lift this indeterminacy? We had similar question in the notion of derivatives. Whenever, do you remember? When I wanted to calculate the derivative of this function for you, then according to the definition of the limit, it becomes this limit. So you already know how to deal with this. I'm just repeating them in an organized way. Of course, in the notion of the derivatives, you always face this limit, but now you don't need to face exactly this limit. Whatever you want, you can calculate if that is indeterminate form. Do you remember what was the trick here? But the same trick will work there.
Like x to the power of 1 over 2?
No, no. I told you the trick. You need to remember. For the notion of limits, it is important. So you need to multiply the numerator and the denominator by the conjugate of the one containing the surd sign. Yes? So what do I mean? Let me change my color. So that would be the solution to this. So if I want to solve that problem, I would write the limit, I would repeat everything, but then I rescale it in a fancy way by 1. How? I multiply the numerator and the denominator by the conjugate of the one that contains the surd sign. Yes? So meaning this. First of all, I want you to understand this equality is a sound equality, yes? Do you agree that this equality is valid? Because this, if I ask you what this is, you would say it's 1. So I'm multiplying this fraction by 1. It means that essentially I'm not changing anything. But why this is useful, you will be patient, you have to be patient and learn this is a trick. If you don't remember this trick, then you will be in trouble. So for the denominator, I formally juxtapose them. I put them next to each other. Yes? But in the denominator, in the numerator, when I want to multiply them, I detect the conjugate pattern. So it becomes the first one squared, which is useful because I get rid of that surd sign, minus the second one squared is 9. X goes to 9. And now you realize what is going on. This was the culprit of this indeterminacy here. And that is now gone away. Yes? So what is left in the numerator, and by the way, let me just repeat, you have to carry on this limit sign over and over again until the very last step. So the numerator is 1, and the denominator is square root of x plus 3. And now x goes to 9. So that reason for indeterminacy are gone away, and that was x minus 9. And now hopefully this limit is no longer indeterminate. And that is not, because the numerator is 1, so it is not infinitesimal. So then at this stage you don't need to worry, you just plug the number in. The numerator is 1, the denominator becomes the square root of 9 plus 3. But the square root of 9 is 3, plus 3 is 6, so the denominator becomes 6, and then the numerator is 1. So it becomes 1 over 6. Of course, we can make a little bit harder problems. We can, for example, have, let me give you more examples. So for example, number 4, assume that you want to calculate this limit of square root of 5 minus x minus square root of 5 square root of, let me make it harder gradually. So, and then divided by x goes to 0. Okay. So we want to calculate this. What type of limit is this? First of all, you test 0. The denominator becomes 0. What happens for the numerator if I put 0? It becomes 0 again. So this is 0 over 0 in a sloppy language. It is indeterminate, yes? So what I have to do, I have an indeterminate limit in front of me containing square root signs. I learned the trick. So what I have to do, I have to write the limit and then rescale it. By what, can you tell me? What should I write? I need to rescale it by the conjugate of what? Of the one containing the third sign. So what should I write? Yes?
Square root of 5 minus x plus square root of 5.
Yes, plus square root of 5, and then I divide everything by the same thing, not to affect the result. Okay, and then what I do, I just continue calculation. The numerator is a conjugate pattern, so it becomes the first one squared, which is 5 minus x, minus the second one squared, which is 5. But in the denominator, don't bother to multiply them, just put them next to each other. So then what happens? You see this minus 5 and that 5 are simplified. So I am left with negative x in the numerator, x square root of 5 minus x plus square root of 5 in the denominator, x goes to 0. Still, the culprit is not gone away, yes? Because x is the reason for this indeterminacy. You see, if I put x equal to 0, still the denominator vanishes, the numerator also vanishes. But then it is clear, because this x and that x can be simplified. And what is left for me here is minus 1. What is left for me here is 1. Now, the indeterminacy is gone. And now I put x equals to 0. So what happens? The numerator becomes minus 1. The denominator becomes what? Square root of 5 plus another square root of 5. So this becomes minus 1 over 2 square root of 5. And I hope that you see all these limits that I have calculated, except the first one and the previous ones, are all infinitesimal over infinitesimal, but the values are quite different. That's why we call it indeterminate. Okay, let me give you another example of this type, a little bit.
Bubba.
Yes?
Oh, never mind.
Is that okay?
No, I saw it. Never mind.
Okay. Number 5. So, for example, let us put third signs both in the numerator and the denominator. So, let me, for example, write 3 minus x minus 1 in the numerator. I'm supposed to send x to 2. And then let me write x plus 7 minus 3. I haven't seen this type of example in the book. So far we have examples of this type in the book, but not this one. But I just want to tell you that's not hard. The only difference is that I have put search signs both in the numerator and the denominator. So this I consider optional, yes. Okay, first of all, is it indeterminate or not? We have to plug 2 in. So in the numerator, 3 minus 2 becomes 1, square root of 1 is 1, 1 minus 1 is 0. In the denominator is the square root of 9, which is 3, 3 minus 3 is 0. So this is indeed 0 over 0. Yes? So that is indeterminate. So I have to lift this indeterminacy, but I have 2 search signs appearing in the numerator and the denominator. Okay, can you tell me what should I do before I write it for you? Okay, so I just repeat the limit. You know that you somehow have to rescale it, and then your goal in your rescaling is so that to get rid of some kind of search signs. So let us check. Okay, can you give me a hint? What should I multiply? Is it 1 time rescaling, 2 times rescaling, 3 times rescaling? How many rescales do I need? Now here I rescale it once. Yes, both in this question I rescale it once. Here. In the previous example I rescale it once. Because I had only search sign appearing either in the numerator or denominator. But here I have both of them. So
Twice?
Twice. One to get rid of this one, so I concentrate on getting rid of this one, and second I consider getting rid of this one. Instead of doing it in 2 steps, because I'm always in hurry in calculation, I wanted to do both of them together. So I rescale it once by the conjugate pattern of that one, yes, and once more by the conjugate pattern of this one. So first of all, I want you to understand this is valid. Why? Because if I ask you what this fancy way, this fancy expression, it is nothing except 1. And what is this one? It's nothing except 1. So I am multiplying my fraction by 1 and another 1. It will not change. So that is crucial. But now, can you tell me how should I organize them? So I have 3 fractions. I want to multiply. So I have to, in principle, I have to multiply all the numerators. I have to multiply all the denominators. But how should I organize them so that I can do less work? So how should I do that? Of course, it is better, beneficial to multiply these 2 because I myself made it in a way that they are conjugate pattern. So then it becomes the first one squared, which is what? 3 minus x. So let me write all the blue colors. Yes. So this becomes the limit. This one multiplied by that one becomes 3 minus x and then minus 1. But what is left for me is the third expression. And then I have to write it next to them. Okay, I just want to wait for you to see that if you understand this step. Can you digest what is happening? Just for the numerator. Is it clear?
Yes.
Okay. But what is your proposal, suggestion for the denominator? I have 3 expressions. Which one do you prefer to multiply together first? Yes?
The conjugate.
The first one, and the third one.
Yes.
Of course, I can multiply this by that, but I'm making a life harder for myself. So I will take this one and multiply it here. So what would be the answer? The first one squared minus the second one squared. Yes?
In the numerator, What does it say? 3x or
3 minus
x?
6. 3 minus 6.
Okay.
So this becomes x plus 7 minus 9. And what I have to put next to it is the denominator of the middle one. Yes? Okay, I want to wait for you. Do you understand what's going on? Yes or no?
Yes.
Yeah.
But then I have to simplify. From the experience that you got so far, you know that you shouldn't do anything with these two. Because that is not the culprit here. Why? Because if I put 2 here, it becomes 3 plus 3, which is 6. If I put 2 here, it becomes 1 plus 1, which is 2. So they are not the problem here. But let us check here. What is the answer to this part? It is 2 minus x. And then what is the answer to this part? It's x minus 2. Yes? Unfortunately, I cannot immediately cross them over because they are not exactly identical. This is 2 minus x. They are not equal. 2 minus x and x plus minus 2. But you already learned, if you have haven't forgotten, what was the trick? Whenever I need a minus b and I am unfortunate to have b minus a, there is a very simple trick to take a minus sign out. Yes? Is that it? So which one you prefer, it doesn't matter. So let me just write one of them. So I would write the limit in the numerator. I put a minus sign out and then I am allowed to interchange them. So it becomes x minus 2 and then I will have square root of x plus 7 plus 3 and then I divide this by x minus 2 and then I have this third root of, square root of this and x goes to 2. Now I am on the safe side. I can simplify. I can simplify this. It becomes 1 times. I simplify this. It becomes minus 1 times because of these negatives. And now this reason for this indeterminacy is gone away. So I hope that nothing problem is waiting for us. I just put 2 inside. I have a minus 1 here. Dot. I have a square root of 2 plus 7 plus 3. I put 2 here as well. So this is 1 dot square root of 3 minus 2 plus 1. And then just calculate. This is very simple. Square root of 2 plus 7 is 3 plus 3, 6 minus 6. And then this is how much is 1 times 2 is 2. And the limit is minus 3. So you see that this limit is also minus 3. All of them are indeterminate, but the values are quite different. Okay, there's only one last part of the limit that is left. And I want to teach you that one as well, and then we are completely done with the limit part. Any questions here? Okay. So you don't need to be worried. So the limits sometimes are not indeterminate, so you just, like the first example, you just calculate them by putting the numbers in. But if the limit is indeterminate, either they are polynomials, the trick is factorization, or you have these third signs. These are 2 simple examples and a little bit more complicated example. I don't think that is something very hard. Okay, but there is another type of limit, and then we are sending x to infinity. Okay, that is something a little bit you have to be careful. So this, I want to talk about this. This symbol is sometimes in mathematics you see limit of f of x when x goes to infinity, yes, is L. Sometimes you see this symbol in math books. You want to understand what does it mean. Of course, this symbol is called infinity, and exactly like numbers. Sometimes, if I want to emphasize, I would put plus infinity and negative infinity. But as far as I understood in your book, there is no plus sign. Whenever they write infinity, they mean plus infinity. But if they want to mean negative infinity, they have to show it. Exactly like numbers. We always write 2. We usually don't write plus 2. Yes? But if you want to write minus 2, we have to write the symbol. That's exactly the same thing here in infinity. So, first of all, I want you to understand, infinity is just a symbol, it's not a number. So, for example, if I ask you, if you go on the x-axis, if I ask you, can you locate this point corresponding to number 2, it is easy, yes? So what you do, you just go here, this point corresponds to that number. And if you go to the other direction, 2 units, this point corresponds to this number. Okay, if I give you 1,000, of course it would be harder, but if you are patient, you go 1,000 steps to the right, and that point corresponds to 1,000. But then if I ask you where the infinity is, this is not possible to answer. This is why I want you to feel that when I use this symbol, it is not like a number. It's not like a big number. Yes? It is actually telling you how x behaves. When I say x gets approaches infinity, you don't know. Is x close to 1 million? Is x close to 1 billion? Or it is not clear. But it means that you can think in this way. X approaches to infinity means that x is larger than any number, positive number that even you can imagine. Yes? So this is the best way to understand what is the meaning of x goes to infinity. When I say x goes to 0, it means that if I go and find number 0, I will be around that number. But when I say x goes to infinity, you cannot locate a point on the x-axis for which I go and get close to infinity. Yes? So infinity is not a point on the x-axis. But it means that it doesn't matter how much you go to the right, infinity is even farther away. But for negative infinity, it means that I go in the other direction. Is that clear? Yes? So when you see this symbol, this doesn't mean that x is getting close to infinity number, to the number infinity. No. It is telling you that x is becoming greater than any positive number that you can imagine. So x goes to infinity means this. Yes? X goes to infinity means x is greater than any positive integer. This is a very good way to understand this at this level. Okay, so for example, let me test your intuition before I teach you. If I give you this function, 2x, and I send x to infinity, what is your expectation? Do you think that these numbers will get closer to a particular number at the end? Let us set up the table. So x and 2x. I don't know which number you might say. So when you are a kid, might be even 10 is a big number. But now you are in high school. Let us start with 1,000. Yes. So 1,000 is probably a big number. It's quite comparable to your CSN, probably. Yes. That's a good number. Yes. So how much you get? 2,000. Okay. But let me increase the value. And then you get, for example, 10,000. So what is the value? You get 20,000. And if I increase it to 100,000, what do you get? 200,000. But you see that, if I ask you, do you think these numbers are gathering around one particular number? The answer is no. Do you remember? I raised that. But in the previous examples we had, when we were getting closer to some number which was written here, we realized that the values are getting stable around one particular number. And that number was the limit. But here, they are not getting closer to any number. On the contrary, they're also getting very big. Yes? So this means that if I start increasing the values of x, without any bound, it seems that the values of my function are also growing very large without any bound. Yes? So what would be your impression? What is a good thing to write? I'm not saying what's a good number to write there, because there is no good number to write there. If you write 2,000, what about 200? What about 20,000? What about 200,000? Yes? So what is the good thing to write here? Yes? Infinite. Yes? So that is the behavior of this function. So whenever you see this, it means that when I make x very big, the values of my function are actually getting very big without any bound. Yes? Is that understandable? That is what you need to understand from this symbol. But now, can you imagine a function for me, which is the topic of your lesson, so that the behavior of a function is somehow in a way that even though I increase the value for x, if I set up this table, I see that the values are gathering around a particular number. Can you imagine of yes?
1 divided by x if x is approaching
Infinite, exactly. So you see, now if I ask your intuition about this function, you see what I am doing up to this level, I am doing the same. Limit x goes to infinity, limit x goes to infinity. But in this case, I can't consider this function. In this case, I'm considering another function. So let me set up another table for that function to get some intuition about it. So for example, let us start again with 1 over 1. Let us start with 1,000. So what I get is how much? I plot 1,000 here. I get 1 over 1,000. So which is 0.001. Yes? But now, let me increase the value. Make it 10,000. Then it becomes 1 over 10,000, which is 0.0001. And now if I make it, I don't know, 100,000, what happens? It becomes 0.000, another 1. Now, I ask you the same question. Do you feel that these numbers now are gathering around a particular number? In this case, what that number is? 0. So then I would say that the limit of this is equal to 0. Okay? So that is the only thing that I want you to learn today about these limits, because can you give me a rule of thumb? What happens? For example, let me ask your opinion. Can you give me another function with that property that even though I send x to infinity, the value becomes a number, rather other than 0? Can you imagine?
X over x?
No, x over x, x goes to infinity. By the way, what happens is, what is the limit of x over x when x goes to infinity? What is your guess for this?
1.
It's still 1.
Yeah.
Because on the right column, you have x over x, and you choose values, very big values for x. But if you choose whatever you choose, you divide it by itself, so it becomes 1. So it is just 1. Okay, so that is also good. Yes? So we send x to infinity, but the answer is 1. Okay. So can you cook up a recipe? Can you give me a function so that when I send it to infinity, it becomes 1? When I send another function, when I send it to infinity, the limit becomes 2. When I send it to infinity, the limit becomes 3. A recipe of cooking all these sorts of functions. Yes?
Can you say a limit of 2x over x?
No, x over x gives you 1. So
but you multiply that by 2.
So let us write 2 plus 1 over x. It's better. Yes? Because why? The limit of this part is 0. What is the limit of this part? This is a constant number. So when I send it to infinity, what will happen? This part becomes negligible because you are dividing 1 infinitely many times. So nothing will be left at the end. It would be negligible. So then negligible plus 2 is just 2. If I have 3 plus 1 over x, then the answer will be 3. Yes? So remember this fact that intuitively this means that a constant number, this is intuitive idea, divided by a huge number is equal to what? Can you write something according to the terminology we learned today? Yes? Not zero. Better than zero. Of course, infinitesimal. That is the correct way of writing. But of course, people summarize it in this way. C, a constant, divided by infinity is zero. I'm also lazy, and most of the time I write this, but I want you to understand this doesn't make sense at all. Yes? Because division happens between two numbers. But I just told you infinity is just a symbol, it's not a number. So even though, but this I will use it myself. I will call it a sloppy language, but if we have that convention among us, we understand what I mean. This is the real way of doing that, the correct way of writing it. Okay? But then that is the sloppy way of saying the same thing. Yes? So then this is very good. Now let me ask you one question, and then we will be finished. If I ask you what is the limit of this one, how do you answer it, by the way? This is a little bit tricky, and if you can answer this question, it means that you understand everything. So here, I have this fraction, the limit of 2x plus 1 divided by x plus 1, 5, x goes to infinity. Okay? Can you tell me what is the behavior of just the numerator when x becomes very large? What happens to the numerator? Yes?
Infinity.
It becomes very large. What happens for the denominator when x becomes very large?
Same.
The same. So if I ask you, by the way, the book hasn't mentioned that, the numerator, the sloppy language, is infinity, divided by infinity. This is also indeterminate. So in the high school, you learn two indeterminate forms. One of them is 0 over 0. One of them, even though they haven't mentioned it, is infinity over infinity. What do you understand by this indeterminate form? It means that depending to the behavior of the function, the answers are different. Yes?
Can't you claim that the numerator's infinity is larger than the denominator's infinity?
That's a very, very hard topic to do. That's exactly the same thing. So this is infinity, but if infinity is a number, and any number divided by itself should be 1.
Yeah.
But it depends on the behavior of the function. Sometimes it becomes 1, sometimes it becomes 0. This is why we call it indeterminate. But what is the trick? Can you tell me how can I convince everyone in the classroom the answer to this is what? With what trick? The trick is more or less using this idea. If I have a constant and I divide it by a huge number, then definitely it becomes negligible. Whenever you want to calculate limits, when x goes to infinity, you have to use this trick. How? Can you tell me how? How can I benefit that in this problem? Yes?
Can you try to get x out somehow?
Okay, how? Can you elaborate a little bit more?
Like, how to say, bryta ut?
Yeah, yes. So take x out from these two, or divide everything by x. If you divide this by x, what will happen? This becomes 2. If I divide this by x, it becomes 1 over x. If I divide this by x, it becomes 1. If I divide this by x, it becomes 5 over x. And now x goes to infinity. Now I ask you the same question again. This was not clear what happens here, but hopefully for all of you, these behavior of these two parts are very clear. Because I am dividing 1 by a huge number. So what is left is negligible, is infinitesimal. At the level of limits, it is 0. So this becomes 2 plus 0. And then what happens for the denominator? 5 over x is also following the same rule. It becomes infinitesimal, but when I am calculating the limit, I can write 0, and then I have 1. And then this calculation is simple. 2 over 1 is 2. Yes? Okay, now let me give you another example. So I would write minus 5x squared plus 2x, let me write positive, plus 1, divided by 3x squared minus 2x plus 5. X goes to infinity. Okay. If x is a very, very large number, what will happen for the numerator? There is no doubt that the numerator is also a very large number. But you have a little bit of doubt in the denominator. Why? Because there is a difference between them. When x becomes very large, the first term also becomes very large. The second term also becomes large. And then you are calculating the difference. So if I have 1,000,001 and I have 1,000,000, both of them are huge. When I subtract them, the difference is just 1, which is not huge at all. So, but do you think the same scenario happening here in this case or not? This is another thing I want you to understand. No. If I ask you what will happen, this power is 2, the power of x is here 1. This is the terminology. 3x squared will dominate over 2x. It becomes so large that you will not actually find the same values. For example, if I put x equals to 1, the difference between these two is just 1. If I make it 10, this becomes 300. Suddenly this becomes just 20. You see the difference is growing. If I make it 1,000, I don't know, this is 3,000,000 and this is just 2,000. If I put x equals to 1,000 here, it becomes 3,000,000 and this becomes 2,000. So this means that the differences are actually growing. And if I make it very, very, very big, then the difference will be very huge. So don't be fooled by this negative sign. Yes? So if I ask you, what is the numerator, you would say it is infinity. If I ask you what is the denominator, don't bother even think about this negative sign. Still it is infinity. But I want you to understand why we can write infinity. Understandable? Okay, now can you tell me what is the trick for calculating this one now? Here we divided by x. Here do you think I should divide by x? Or a better idea? X will not work in this case. Because if I divide by x, I will get 5x. This will become 2. This becomes 1 over x. If I send x to infinity, this is negligible good. This is too good, but then this is still infinity. And I will have problems. So what x is rather good, but not 100%. So what is good here to divide by?
X squared.
X squared. So if I divide by x squared, this becomes the limit 5 plus 2 over x plus 1 over x squared. And then this becomes 3 minus 2 over x plus 5 over x squared. Let me give you time. Do you understand what's going on? I divided the numerator and the denominator by x squared. Agree? But is it useful now? The answer is yes. If I ask you what can you do with this part, what is the answer? When x goes to infinity?
Negligible.
0. Negligible, which in the limit we say 0.
Yes.
1 over x squared, what will happen for that one? That's also 0. It's even better. Because infinity, you square it. It becomes very bigger. So that is also, so this goes to 0, this goes to 0, this goes to 0, this goes to 0. So what is left is 5 and then 3. That is very interesting behavior, by the way. This function, even if you bother yourself to make x very big, you cannot make this fraction bigger than 5/3. When you go, it might happen that it goes higher than 5/3, somewhere in middle. But if you wait enough and go to the right, very far to the right, the value would be around 5/3. Yeah, so it doesn't matter how big you make this, this becomes closer and closer to 5/3 only. Yes? Any questions? Okay. So, yeah, I will write on Google Classroom which parts of the previous chapter is related to these exercises. And then if you have questions, I don't know, one of those sessions that is left, I want to teach the next chapter, because if I want to wait for 3 more sessions for you to practice and do that, it will be quite behind schedule. Thank you very much.
Thank you.